So today's lecture is a parallel operation of two alternators. So parallel operation to alternators. So in the previous lecture, we already discussed what are the advantage of parallel operation. In short, the parallel operation advantage is operating cost, because there are different type of generating plants are there. It may be a thermal power plant, hydropower plant, nuclear power plant. So if all the power plants are connected together, definitely the operating cost of the alternators or operating cost of the plant is smaller. Second is the maintenance. It is easy in maintenance. In a dry season, that is in the summer season, we can do the maintenance on hydropower plants. And when ample quantity of water is available, that is in the rainy season, the entire load can be shifted to the hydropower plant, and we can take out some of the thermal power plants for their routine maintenance. And third is the economy and the utility of the system. We can utilize the system very well. If there are a single unit generator is there, single large unit generator is there, in night time or in from night hours or off peak period, the operating cost is very high, or we cannot utilize the entire capacity of the unit. That is a unit means it is a combination of turbines and say alternators. All these things are there. And whereas when the generator is going to work at say a proper efficiency only when it is properly loaded, say 80% loadings are there. So if we are having large number of generators or the multiple generators, they are connected in parallel, definitely we can utilize the proper capacity of the generator. And next is the continuity of supply. Okay, so these are the some advantages we have already discussed in the previous lecture. Now we want to see the operation of two alternators when they are working in parallel. Working in parallel, already discussed that it means that two alternators are there. Two alternators are there whose output is connected to the common load. Output is connected to the common load. Say this is the alternator whose value is EF1 and whose value is EF2. Definitely it is connected with the prime mover. It is connected with the prime mover 1 and prime mover 2, and it having some excitation current is there. So it is some exciting circuits are there for the generator 1 and similarly generator 2. So there is an exciting circuit, and it is connected with their internal impedance, that is impedance and resistance of the generators are there. Impedance, it is consist of resistance and reactance. So XS1 into it is RA1, and here XS2 RA2, and it is connected to the common bus. So this is the common bus. Okay, now it is common bus, it is connected with the load. So this is the load is there. It's your load. Again, load is comprises of resistance, and this one it having some impedance, it is ZL. So this is the say simple two generators are working in parallel. Now our objective in this lecture is to examine what is the effect of change in excitation. This is the excitation. If you are going to change the excitation of one of the alternator, what is the effect under load condition, under no load condition? Similarly, what is the effect of change in mechanical input? What is the change in mechanical input? So what is the effect of what is the effect in the load, what is the effect in the operating parameter of the alternator, that is the frequency, power factor, terminal voltage, reactive power. So this is our points to be examined by changing the excitation and by changing the mechanical input. Okay, so this is the things which we have now considered. Now under such condition, say this is the terminal voltage, Vt is the terminal voltage, and EF is the EF1 and EF2 is the exciting, it is the exciting current, and here the current delivered by generator 1 is IA1 and generator 2 is IA2, whereas the total load current is IL. So IL is the combination of IA1 and plus IA2. Definitely it is a vector addition because we are dealing with the AC current or AC quantities are there. ठीक है. Now, first effect we will want to see what is the effect of change in excitation. Effect, first of all, we see the change in excitation. Effect of change, effect of change or changing in excitation. Okay. So for this purpose, what we will do, we will try to draw the phasor diagram, and from the phasor diagram it becomes very simple to understand what is the effect of change in excitation over the alternator. Okay, so say we can draw this as an equivalent circuit. Equivalent circuit of generator 1 is, say this is the say here it is a resistance, inductance and exciting current or exciting voltage. So this is represented as a ZS1. Now the second generator, resistance, inductance and exciting voltage, EF1 and EF2. So it is a EF1 and it is say EF2, and this is nothing but a Z2 or ZS2 is there. They are connected in parallel with the common load. So here it is connected in parallel. So now these two alternators are in parallel under no load condition. So this is the excitation voltage, and here we can say that this is the terminal voltage Vt. Terminal voltage is Vt. Now we can connect a load on the alternator. So we want to examine what is the effect under no load condition and what is the effect under load condition. Okay, so this is the load is there, it is ZL, and when it is delivering the current is IL, whereas the current delivered by first generator is IA1 and the second generator is IA2, isn't it? So this is the some equivalent circuit of parallel operated generator. No doubt we have omitted this part, that is a prime move 1 and prime move 2. Similarly, the excitation circuit 1 and excitation circuit 2. It is assumed there is excitation circuits are there. Okay. Now, when the two alternators are in parallel, what is the condition? What is the condition for the parallel operation? Number one, the voltage should be same, phase sequence should be same, and third is the frequency should be same. Okay. Now, when all these are same, we can say that the generators are working in parallel, or this is the parallel condition of the alternator. Now, under parallel condition of the alternator, we can say that the excitation voltage EF1 and excitation voltage is EF2, it is same and they are opposite to each other, isn't it? And therefore no resultant voltage between the local circuit. So first of all, we have to understand what is the local circuit. So this is called as a local circuit. This is called as a local circuit. Okay. So and the local circuit, we can say that the voltage across voltage induced in EF generator 1 and generator 2 is same. So we can represent as a local circuit. So voltage induced, okay, try to draw state 1. So here the voltage induced in EF1 is equal to EF2. It is EF1 is equal to EF2 and they are opposite to each other, and in such a way that the voltage between this local circuit is 0. Okay, and from the external side we can represent as this is the say this is the voltage EF1 and EF, that is it is called as a external circuit voltage. Circuit voltage, and it is called as a local circuit voltage. Local circuit condition, isn't it? Now suppose by any change in the parameter, what happen? The EF and EF2 will not be same. Definitely EF may be greater, EF2 may be greater, and under such condition some circulating voltage is going to develop, and that is EC is equal to EF1 minus EF2 or EF2 minus EF1, which is the greater value. This voltage exit in the local circuit. So first of all, we have to understand what is the local circuit. Local circuit, this is two are there, and because of these two local circuit, the current is going to circulate, that is called as a circulating current, which is equal to EC, that is the circulating voltage, divided by what is the total impedance of this circuit? It is the Z1 and Z2. So it is ZS1 plus ZS2. In some previous lectures or many lectures, we come to know that in case of the impedance of the alternator, Zs is equal to synchronous reactance plus armature resistance Ra plus Jxs, synchronous reactance. The synchronous reactance value is large. Synchronous reactance value is large as compared to the resistance, isn't it? Or if the resistance is ignored, the circuit is dominantly inductive. It means that the circuit comprises of only inductance, and when the circuit comprises of inductance, current going to circulate which is lagging by 90 degrees. Okay, so now we will take the example. The example is such that the excitation of alternator, our objective alternator excitation of alternator 1 is increased. We have increased the EMF or increase the excitation of alternator 1. This is here we have increased the excitation. Okay. So what happened? Definitely the magnitude of EF will be greater. Under such condition, definitely the excitation voltage EF1 is greater in magnitude with the EF2. So under such condition, what would be the phasor diagram? So under such condition, the phasor diagram is like that. say this is the EF1 and it is EF2, both are same at exact parallel operation under parallel operation condition. Now the excitation of the alternator has been increased. So here there is an increase in excitation voltage. There is an increase in excitation voltage. Here say we have increased the excitation voltage, which is known, we have given the name is EF1 dash. We have increased the, so under such condition, it will circulate the current which is lagging by 90 degrees. So where will be lagging? Always anti-clockwise direction. So this is the increase in voltage, which is equal to EC, which is equal to EF1 minus EF2. EF1 minus EF2, this is the change in terminal voltage, the excitation voltage of the generator, and therefore some difference of voltage is going to exit in the local circuit, and this local circuit will circulate the current IC, which is equal to IC divided by ZS1 plus ZS2. But where will be the IC? Definitely it is lagging by 90 degree with respect to the voltage EC. So here if you develop, if you see, if you represent, this is the excitation voltage in the local circuit is EC, therefore the current is lagging with respect to this one, say it is 90 degree. So it is lagging by 90 degree, okay, with respect to IC, or the current IC is lagging with EF1. We'll write here, say IC is lagging with EF1, whereas IC is leading with EF2 by 90 degree, by 90 degree, by 90 degree. Okay, quite clear? See in this, because this is a very basic one to understand, because there are multiple topic which is related to this local circuit voltage, lagging current, leading currents are there. So again I will repeat, under parallel operation, the voltage induced in generator 1, that is EF1 and EF2 is same. In the external circuit, it is represented by a single voltage EF1 and EF2 in the same direction. But in local circuit, we are it is represented as both voltages are opposite to each other, and when their voltages are opposite to each other, the circulating voltage is zero and there is no circulating currents are there. But as soon as if we have increased the excitation of one of the alternators, say the alternator 1, the magnitude of EF1 is become greater than EF2. This is EF1 greater than EF2, and because of these two, circulating voltage comes into the circuit, in the local circuit, and it will circulate the current IC. This will circulate the current IC. Now this circulating current is lagging by 90 degree with respect to EC. Why it is lagging by 90 degree? Since the resistance is say it is very small as compared to the reactance, and the local circuit impedance become inductive, and inductive current draws the lagging current. So here the current is lagging by 90 degree. Now if you just look at to this figure, this equivalent circuit, we found that this circulating current not utilized by the load. Even suppose it is connected with the load, that circulating current only circulate in the local circuit, in the circuit of generator 1 or generator 2, alternator 1 and alternator 2. It is not utilized by the load. So this circulating current, if suppose this circulating current is very high, it will increase the resistance loss, that is a copper loss, and it will heat the generator, and we can say that the generator become overloaded. Even there is no appreciable load on the generator because the current is high. and the low kVA ratings or VA rating of the generator become sufficient, say to its rated value, even though it is not loading the, it is not supplying the load to the external circuit or load circuits are there. Okay, so now come to the our effect of armature reaction. Just recall that effect of armature reaction. What is that? The armature reaction is magnetizing, demagnetizing. It is depend upon the nature of current. Here, the IC, it is leading with the EF1. So we can say that here, in between these two, the armature reaction is magnetized. Here, the armature reaction, sorry, it is lagging. So the armature reaction is demagnetized. So here, the armature reaction is demagnetized. Okay, and whereas IC is leading, so when there is a leading, the armature reaction is magnetized. So under magnetized condition, the alternator voltage get increase, and under demagnetized condition, the armature voltage of the alternator get decreases. So this current is demagnetized for EF1 and it is magnetized for EF2. So we can say that the circulating current tried to reduce the magnitude of EF1 dash, and whereas it will try to increase the magnitude of EF2 in such a way that two voltages become equal, and as soon as the two voltages become equal, the circulating voltage becomes zero as well as the circulating current becomes zero. Okay, so now this circulating current, it is called as a synchronizing current. Why it is called as a synchronizing current? Because it tried to maintain the synchronism between two alternators by magnetizing one alternator and by demagnetizing second alternator in such a way that the magnitude of first alternator decreases and magnitude of second alternator get increases, and once it is become equal, the circulating current get disappeared. Okay, so therefore it is called as a synchronizing current. So the objective of the synchronizing current is to bring the alternators again into the synchronism up to some extent. No doubt, if you have increased the excitation very large, so there is a very large change in the excitation current, excitation EMF, and this circulating current is tremendously high. Instead of bringing two alternators again into the synchronism, it may burn out the one of the alternators or both alternators are there, because small voltage will lead a heavy current. Why it is? Because we know that here the it is just like a short circuit. It is just like a short circuit. Suppose the reactance voltage is 10 volt, EC is equal to 10 volt, whereas the impedance is equal to say only 1 ampere, 1 ohm is there, so 10 ampere is there. Okay, if the impedance say 0.5 of both alternator, the current is 20 ampere. So even though a small value of circulating voltage, there is a large value of circulating current. So this is the condition under no load. Now under load, what happened? What would be the change under load condition? So it is a long discussion, but okay, second we will take under no load condition, what would be the effect of change in mechanical input. Okay, so second topic is effect of changing mechanical input. Definitely it is for the no load. No load. First we will discuss no load condition, then we will discuss the load condition. Again, the system is same. means it comprises of resistance, impedance, and excitation 1, EF1, it is ZS1, and this is second alternator, ZS2, excitation EMF is 2, and both are in parallel, and again under no load condition. Under no load condition is there. But under no load condition, the terminal voltage is VT. So external circuit and internal circuit is same. That is, this is the internal circuit or local circuit. In the local circuit, both voltages are equal in magnitude and quite opposite to each other. So this is your EF1, it is EF2. This is for the, say it is for the local circuit. Whereas for the external circuit, it is, we can represent as this is the external circuit where EF1 and EF2 is same. EF1 and EF2 is same, and it is represented. Now, when we change the mechanical input of one of the alternators, say for example, we have changed the mechanical input, prime mover, we have increased the mechanical input. Once we change the mechanical input, the excitation voltage will remain same. So after change in mechanical input, EF1 and EF2 will remain same because the excitation voltage is depend upon the excitation current. If you are changing the excitation current, then and then it is going to change the excitation voltage. Otherwise, the excitation voltage will remain same. But what are the change? The change in the the voltage is going to ahead. Voltage is going to ahead by the same magnitude whose excitation, whose mechanical input has been increased. Say for example, here the mechanical input of the first alternator has been increased, so it is get somewhat ahead. So there is some mechanical angle change is there. There is a mechanical angle get change, whereas the magnitude of voltages are remain same. So here EF1 is get advances, and because of this advances, the voltage is going to develop in the local circuit, and it is represented by EC. This is represented by EC. Okay, this is the change when we change the mechanical input, and say this angle is whatever the angle is there. Now we can represent it by in this fashion in this circuit also. So under such condition, the mechanical input of the first generator is going to change. So it is shift the value, shift the angle. Here it is the value is EF1 dash is there. Magnitude is same, so we will write only the EF1 is there. And because of this one, the vector addition of these two, say this is the vector addition, and here we will represent it as EC. This is the EC. We have shown here. This is the circulating voltage is going to develop. Now, whenever there is a circulating voltage, there is a circulating current which is lagging by 90 degrees. So this is the vector diagram, anti-clockwise direction. So here the circulating current will be here. Okay, so this is represented by say this line. This is the circulating current, IC. Now see, this circulating current has a small angle with respect to the EF1. So I write here EF1 and IC has angle, say angle is theta1. Okay, this theta1 is smaller than 90 degree. whereas EF2 and IC has angle say theta 2, which is greater than 90 degree. So this angle is theta. So the angle which is less than 90 degree, it is acting as a generator, and whereas it is acting as a motoring mode, and the it is acting as a generating mode. Okay, so the machine which is acting as a generating mode, it get retarded. Here the machine one acting as a generating mode. So when the machine acting as a generating mode, and it will try to retard its speed, and hence again we can say that it come to the equal, say it again come to the angle between its again become is equal to 180 degree. Okay, whereas the generator 2, it is acting as a generating mode, the second machine acting as a generating mode, so it will just some one is there. Here, which generator, which voltage is smaller? Yes, this voltage is smaller. So it is going to supply some of the load positive, while it is and so here it is a second one machine acting as a motoring and second machine acting as a generating, and the equivalent effect is that it tried to bring the accelerating machine in such a way that the two machine again come into the synchronism. So this is the effect of change in mechanical input under no load condition. So what is the change in the load condition, we will see in the next time. So it is the effect of one machine acting as a motoring, second machine acting as a generating, and equivalent effect is that both machine come into the again synchronism. Now effect of change of excitation for load condition and effect of change of mechanical input in the load condition, we will see in the next time.